Thank you very much. Thank you very much for inviting me to give this talk. I will talk on non-commutative minimal surfaces, and I will give a very naive sort of bottom-up approach, which reveals the motivation we had for studying this problem, which comes more from solving non-commutative equations than from starting from algebras and trying to identify minimal surfaces. But these things can be lifted to a more natural algebraic language, which I will do at the end. But I will start very naively. So this is joint work with Jens Hoppe and Jaegyang Che. Jens Hoppe in Stockholm and Jaegyang is in Korea. And we have a preprint on non-commutative minimal surfaces, and there is also some work in progress going on, which I will report on. So let us just remind ourselves what are minimal surfaces in the classical setting in geometry, right? So a minimal surface is an embedded surface, which we call the vector x here, such that the induced metric gives an area of the surface which is minimal, stationary with respect to variations. It doesn't have to be minimal, but stationary. So you try to vary this area functional and you try to solve the equations, and you get a minimal surfaces, classically minimizing the area. So this can be formulated in many ways, like mean curvature 0 or whatever, but one way we will consider is that actually if the embedding coordinates are harmonic with respect to the Laplace operator on the surface, then it will be a stationary point of that area functional. Right? So this is one way of doing it. Right, so why do we want to do non-commutative minimal surfaces? Well, first of all, the classical theory of minimal surfaces is very old. I mean, I don't know, more than almost 200 years, 150 at least. And it is a rich subject. It contains many, many results, many examples, and it's a very nice piece of mathematics and surprisingly quite active still. Okay? So, but from a purely mathematical point of view, it's interesting to see if can we do something as nice with non-commutative geometry as you can do for classical geometry, right? Because these surfaces are special. Maybe there are special objects in non-commutative geometry that would be nice to work with. And now coming closer to our original motivation is that there are zillions of explicit formulas for minimal surfaces, for instance in R3, let's say. And these can be turned into non-commutative explicit minimal surfaces that you can use and compute with. So this allows one to construct many, infinitely many explicit examples and try to work with them. And also an infinite number of solutions of certain equations. And moreover, so kind of minimal surface equations or varying the area and looking for stationary points is very common in physics. For instance, membrane and string theory does this when you start out at a classical level. And equations that arise when you try to quantize these systems, they have equations that are similar to, or they are non-commutative analogues of the Laplace operator. So maybe for physicists, equations like these double commutator equations where you sum over two of the indices here, k, might look familiar, and you want to look for solutions to such equations. And this kind of trying to solve equations was one of our original motivations for starting this. So let us slowly approach now non-commutative minimal surfaces, and to do that we would like to reformulate a piece of geometry in terms of Poisson brackets, okay? To find the right kind of formulas that you want to generalize from ordinary geometry to the non-commutative algebra. So we just some notation. So we have a two-dimensional manifold called sigma. It has local coordinates u and v, and it's embedded into Rn, and it gives you an induced metric as written here. And we have two kinds of indices, indices A and B. They live on the surface, goes from 1 to 2, and index I, J, K, and so on. They live in the ambient space in Rn, let's say, and they run from 1 to n. Okay? And you can introduce a Poisson bracket here in local coordinates for some density rho. And for convenience, we introduce now a no, okay. Sorry, this gamma here. It's square root of g over rho, which measures the difference from choosing rho to be square root of g, which is a natural choice, a natural density, and choosing something arbitrary. That's called gamma here. So we have a surface, we have a Poisson bracket in the standard way. So, and we get the Poisson bivector. That's usually this combination of the density and this epsilon for surfaces. And one simply notes this formula here with the product of two thetas, which is just rewriting in principle the fact that the complex structure squares to -1 on a Cayley manifold. Not quite -1 because we have the gamma there, so it's slightly rescaled. But nevertheless, it's just one way of writing that. And for surfaces, this is just simply prove with the epsilon tensor. Okay, now I claim that the geometry of the submanifold sigma can be expressed in terms of Poisson brackets. And this follows from a simple observation that the projection operator taking a tangent vector in the ambient space down to a tangent vector on the submanifold or the surface, this projection operator can be written, it's called P here, and this can be written as you see here, solidly in terms of Poisson brackets, of the embedding coordinates, and of course of the components of the vector you are projecting. So every derivative in this expression lives in a Poisson bracket. And that's, by the way, what I mean when I say a reformulation of differential geometry in terms of Poisson brackets. I mean that every derivative that appears is a derivative inside a Poisson brackets. So there are no free dAs floating around. Everything can be computed algebraically, if you wish, from the Poisson structure.
But this is not an invariant definition.
Pardon?
It depends on embedding.
Sure. The embedding coordinates gives you the metric.
Metric cannot be defined in terms of Poisson structure in general.
The induced metric, I'm always considering the induced metric. So actually choosing the x's gives you a choice of metric. Yeah, that's important, right? Pardon?
This Poisson bracket is the one from the surface. So
right.
X is practically extra functions of the surface, right?
Right,
Yeah,
right.
Yeah.
Yes, they are the embedding point. And this you can do not only for surfaces, but general submanifolds of general ambient manifolds. And we did this in two papers I quoted down here. It will not be important for my talk. I just want to put it in a slightly bigger context. And for general n-dimensional manifolds, you need actually an n-ary bracket. Unless you have a Cayley manifold, you can do with the Poisson bracket. Okay. So you can actually formulate geometry of the submanifold in terms of Poisson brackets. So why do I want to say this? Well, in particular, let's take the Laplace operator on the submanifold, on the surface. Now, in the same spirit as the last expressions, you can write these in the following two forms. As a double Poisson bracket, either including the embedding coordinates or the local coordinates on the surface, right? So this you can simply directly prove if you like. You don't need the rest of the theory. Simple. And furthermore, on a surface now, you can always find conformal coordinates. So conformal coordinates are coordinates such that the metric is diagonal and the two diagonal elements are equal. The two functions there are equal. Okay, so let's assume we choose such a parametrization. And we choose a Poisson bracket in a particular way with rho equals 1. And you can write the second equation above as the sum of the two double commutators as you see on the last line. Okay? Double commutator with u, and with v and v. And this will give you the the Laplace operator acting on a function f on the surface. Okay? So nothing strange here. It's simple. So, as I said before, minimal surfaces can be characterized by the fact that the embedding coordinates are harmonic, Laplace of xi equals 0. And in conformal coordinates, we can write the Laplace operator in this particular way. So we can define a minimal surface, as is done in some minimal surface books, simply directly in terms of conformal coordinates. Namely, a surface is minimal if the embedding coordinates are harmonic, can be written in terms of the Poisson brackets, and in this very particular coordinate system, we need to ensure that the coordinates are conformal, that the metrics satisfy. These are the components of the metric right here. So the off-diagonal blocks are 0 and the diagonal blocks are equal. Right, so this is how you could state the problem of finding minimal surfaces in Rn. And this is the starting point now for our first naive search for non-commutative minimal surfaces. We simply want to generalize these equations, okay? And now, before doing that, let us introduce the algebra we will work with to start with, namely the Weyl algebra. As most of you know, the Weyl algebra consists of two non-commutative elements satisfying this commutator relation for some real number h bar different from 0. Call this the Weyl algebra. And the Weyl algebra satisfies the so-called OR condition, which means that you may embed it in a field of fractions, right? So we will both have the Weyl algebra, which is called AH bar, and the field of fractions, the fraction field, so rational expressions in these things, which will be called FH. Okay. Right? It's moreover, it can be made into a star algebra by declaring these to be Hermitian. And just for notational reasons, we just see the real and imaginary part of any element, right? And we have two derivations, which are the commutators with v and u. I call them du and dv hat. And they commute. Since u and v commute to 1, these derivations will commute. Which is, of course, in complete analogy, if you want to, with the fact that the ordinary derivatives can be written in terms of the Poisson brackets like that, right, in geometry. Okay, some more notation simply. So in analogy with complex analysis, we just take lambda to be the complex combination of u and v. We introduce d and d bar, as in complex analysis, to be the du minus idv and du plus idv. And still they commute, of course, since d1. du and dv commute. And now some terminology that we need for this talk. So it's, of course, it can be natural to call elements that are annihilated by the d bar derivative, to call them holomorphic. And we will. But here it's also the possibility of having irrational expressions being holomorphic, which we would, of course, call meromorphic in the complex analysis. But now we won't see anything about these if there are zeros in the denominator and so on. So we simply call these now rational holomorphic, because they are still annihilated by d bar, but they will actually be rational expressions in polynomials in this lambda. Okay, so we just call them R holomorphic. So any polynomial in lambda is in particular holomorphic. So it's like the variable z. Now we define the Laplace operator in analogy with the classical expression. So we just replace Poisson brackets by commutators, and or 1 over I h bar times commutator, and this is what you get. And we simply call things harmonic if it's annihilated by this Laplace operator. And this can be, of course, be written in the usual way as dd bar on an element instead of this sum of du squared and dv squared. Okay. So what would we like to do? So we had a particular formulation of a minimal surface that we would like to generalize to the non-commutative setting, namely this one. So we had harmonic elements, so Laplace of xi is equal to 0, and the fact that the parameterization was conformal. So these scalar products here has to vanish and 2 have to be equal. And let us start now by turning this into the most naive definition you could ever imagine. So replacing small letters by big letters and Poisson brackets by commutators, right? So you take an n-tuple of Hermitian elements in the algebra, and here is the fraction field of the Weyl algebra. You call it a non-commutative minimal surface if it is harmonic. Every xi is harmonic. And now these E, G, and F, they are the components of the metric in quotation marks. Now for this, there are simply sums of derivatives of xi's, just as the classical expression, with a slight symmetrization of the off-diagonal elements. The other ones are symmetric, of course, since it's the same derivative, du. Okay, so you may think, well, what to do with this? Can you now do anything with this definition? I mean, you can define anything, but you want to be able to do something with it, right? So this is, of course, very not so much non-commutative geometry, right? It's very naive formulation. And, but the nice thing here is that you can actually now prove some analogues of classical theorems for minimal surfaces. For instance, in R3, for minimal surfaces in R3, there is Weierstrass representation formula. It tells you that every minimal surface in R3 can be written in a very particular form, an explicit form, so to speak. And these are exactly all the minimal surfaces you can get. Now, with these definitions, you can actually prove the same theorem for non-commutative minimal surfaces, giving you, if you don't like the word surface, giving you a solution to such Laplace equations, infinite many number of solutions. So this is the theorem you prove. So now you take 3 elements, and you have to have some technical condition which is already there in the classical case. You want to exclude planes and so on. Then you can find elements in the Weyl algebra, f and g, which are holomorphic, and some numbers x1, x2, x3, such that your surface can always be written in the following form. Now the integral here is simply just the antiderivative with respect to d, the d operator. So there is nothing fancy going on. It's simply antiderivative, right? So, and conversely, if you take any f and g, you plug them in there, and you can actually integrate these 3 expressions. There you have your minimal surface. So it already gives you a lot of minimal surfaces with this definition. Okay? So this was sort of some of our motivation for doing this, that you can produce explicit solutions to these equations that you can work with and play around with. Okay? So I'm just stating this theorem now, so I am not saying anything about the proof, but the proof in principle goes through with some modifications as the proof you do for minimal surfaces in classical geometry. Okay, so now just some remarks on this R-holomorphic and holomorphic. So to get this general representation theorem, we actually worked in the fraction field of the algebra. So we were able to invert things, and that's, of course, otherwise it may not be possible to write every minimal surface in that form. It is still true that if you choose f and g and you write this down, this will be a minimal surface, but the other way around might not be true if you have to invert things that are not invertible. Therefore, we have to do in the fraction field. However, this is not limited to the fraction field. You can if you just say that every combination of operators or elements in the algebra that I need is invertible, then everything is fine, right? So if you want to work in a representation of the Weyl algebra, and your operators that you are considering are invertible and so on, it's no problem. Now the xi's don't have to be invertible, of course, but something have to be invertible.
Is this field of rational convertible function kind of finite extension of some natural field we can attach, like in classical case?
No, I don't think so, but I'm not sure. I don't.
Surface is a finite extension of
right.
rational functions.
Yeah. I don't know, but I don't think so. Yeah. Okay.
Rational functions are functions. Rational functions on the plane. This is function on the plane. So this is
Yeah.
your minimal thing you're starting from. Couldn't now look
Right.
at more general things, but maybe taking extensions of the fraction field.
Right. Tensor products, and then taking quotients. You can perhaps do right. Yeah.
That's your fine thing.
Okay, that's what you mean. You could imagine start tensoring these things and take quotients and so on. Right. That's right. That's right. Now I understand your question. Right. That's right. Yeah. Okay. This is what I said. If you don't like the fraction field, you may just work with things that you make sure that they are invertible. And I want to point out once more, with the help of the theorem, you may generalize many classical minimal surfaces to non-commutative ones, and to get many solutions. Okay, so that was sort of the first very naive part, what you can do, which reveals our motivation, as I told you. Now we want to put this in a slightly more algebraic language to generalize it to other algebras, to other ambient spaces, and And then we need to reformulate it. And also we want to do some more geometry and curvature. And so we have to have these things at hand. So we simply start from we want to reformulate the previous problem. Instead of the x's being harmonic and the parameterization being conformal, we will want to reformulate it slightly. So Fn denotes the free right module with the canonical basis ek here. And starting from our x's, instead of x's, we can take the derivative of the x's and take them as elements of the module, the free module, by simply taking as ei dxi, as written here. And the conjugate also, where you take the conjugate of the component, like this. So this is also very close to what you do in geometry.
So this is a model over what?
Over the fraction field of the Weyl algebra, or the Weyl algebra. Yeah, but right now, but you may forget it because later on we won't just consider the Weyl algebra, right? But right now it is. And we want to have sort of a metric or a skew linear Hermitian form like this. So this is the very simple one. Of course, you always take on free modules. You conjugate the first one, multiply by the second component, and you sum of the components, right? So now you can reformulate the property of being a non-commutative minimal surface then in the following way. So if you take the phi to be the derivative of the x, you can say that the d bar phi I equals 0. That's the equivalent of x being harmonic. Remember, phi is dx, so this is d bar dx, which is the plus operator, equals 0. So that's the fact that it's harmonic. The second one is simply rewriting the fact that it has a conformal parameterization. So that h of phi bar comma phi, if you write it out, you can identify these E, F, and G, and you can see it's the same thing. So you see here, if you like now, you can completely forget about xi's because they are just obtained then by integrating the phi's. Okay, you may ask, can I integrate the phi's? Okay, but if we don't care about this, we might as well look for phi's satisfying this thing. Because the integration we may be able to do, may not, but that's not so important for us right now. Okay. So let us take some examples. I told you many times now there are many examples. So let us just write down some examples. So in R3 we can produce many examples. These are of purely algebraic nature, these ones. So the phi is now the components of phi, which is a vector in the free module. Its components depend only on the lambda, which makes them then automatic d bar of phi I equals to 0, because d bar is the commutator with lambda. Since everything commutes with lambda, it's trivially so, right? So for any polynomial f, this combination here gives you a minimal surface. In classical geometry, the choice of this polynomial b is equal to 1, so the most trivial one, that's the Oedipus surface, which is usually called. Let us just write this down to see what we get. So this is the data giving the Oedipus surface, these two elements of the free module. And these we can integrate. I mean, all these algebraic surfaces we can actually integrate to find the x's. And if you want to write the x's in some normal ordering with u always to the left, it becomes this expression here. And now at this stage, it is not immediately clear that these expressions here satisfy the double commutator equations. So now, and this is, I mean, many of these theorems, they're not hard to prove, but once you go to explicit things, it's not so clear anymore that you would have thought of these without doing the abstraction first and then coming up with explicit examples first. Okay. Moving slightly away from the Weyl algebra into a representation of it. So these examples were algebraic. Now you could sort of, many of these minimal surfaces, they are given by analytic functions, right? So let's just take the simplest one, namely the catenoid in R3. That's a minimal surface going like this up. And let's try to just see if we can do something with it. So classically, you have the following data defining the catenoid. And now, of course, sinh and cosh, which are the hyperbolic trigonometric functions, they don't exist, of course, in the Weyl algebra. But you can imagine going to a representation and defining them, for instance, like this, with e to these elements. Note that there is no I here. They're not unitary operators. They're e to these u's and v's. And you can make sense of all these, and you can find the right domain of definitions, and blah, blah, blah. I won't care about this at all. I'm just saying that you can do this, right, in a representation. You can take e to the operator with a suitable domain of definition, and you can readily check that the two conditions are satisfied. The commutator, the d bar of phi I is sort of trivial because it's a commutator with lambda, and everything depends only on lambda. But the non-trivial condition to check is the fact that it's conformal parametrization, that this inner product, or what you would like to call it, is 0, and this you simply compute it to be 0. So it also works. Now, let us go to more general things, and let us find a more general definition of a minimal surface. And for this, we need to review slightly how does it work when the ambient space, the space that the manifold sits in, is not simply Rn. Right? Okay? So if it's simply not Rn, but you still want to have a stationary point of the volume functional, you want to vary it and find stationary points, and you get this equation written here. So you get the Laplace operator, but you get corrections which has to do with the curvature of the ambient space. Gamma bar is the Christoffel symbols of the ambient space Levi-Civita connection. Right? So it has the curvature of the ambient space in it. This is the equation. Now we want to turn this one into a non-commutative definition. And for conformal coordinates, you can simplify this expression. And you simply get this sum of the covariant derivatives. And EU is now the sort of the standard vector, du xi, and EV is in the other direction. And the nabla bar is the connection in the ambient space now. Not on the surface, but in the ambient space you have the connection. So that's sort of given data, given an ambient manifold with a metric, given its Levi-Civita connection. And this is what you get as a when you write down the condition for it to be minimal. Now this looks much better, right? Because covariant derivatives, that's a natural object for modules. So this has a good chance of being generalized. So let us try to do this. So we just change now our basis to these complex vectors. Instead of du and dv, we take these complex combinations of the two vectors. And you just write the previous condition now as this condition. So now they are mixed instead. The covariant derivative of phi in direction of phi bar plus the opposite is equal to 0, which generalizes the previous condition that simply d bar of phi I is equal to 0. Okay? We still have to supplement this with the fact that the parameterization should be conformal. So you should have conformal coordinates in some sense. And this is now the same condition, right? We write down the same condition here. Now H is no more the simple free module Hermitian form, but can be something arbitrary, satisfying, of course, the usual things we want from a Hermitian form. Okay. So let us just fix some notation for what we want to do now. Sorry, before I go here. Now it's sort of obvious what we want to do, I hope. So you want to take some module with some connection, and you demand these two things. And you call that a non-commutative minimal surface.
What is small h?
Small h is an Hermitian form, so it's a skew linear map from the module, two elements of the module into the algebra, and it also satisfies the right linearity for the right modules. So this, I always assume that. I will now, next slide, I will precisely state what I assume about these things, okay? But I hope the picture is sort of clear. So if you don't, you can think, okay, why is this a manifold or so? But you can think of it like this instead, that I pick two vector fields, phi and phi bar. And now I want to compute geometry of this distribution. I mean, at every point it chooses a vector space, and that goes on in the manifold. And I want to simply compute the properties, the curvature of this distribution, right? So I forget about the manifold. I just look at some distribution in space. So that's what I'm doing here. Okay, so now we fix the notation. So we take a star algebra A, no longer the Weyl algebra, just any algebra, star algebra, and we take M to be a right A module, and now we have this skew Hermitian form H, which fulfills this star symmetry, and also it's linear in the right argument, right linear in the right argument, like this. Okay. And we let nabla bar be some affine connection on M. So I mean, for every derivation, and we think of nabla D as a map satisfying these properties here of an affine connection, together with some linearity in this little d variable. Okay, so the standard, just standard things. And we also will now assume that it is a Hermitian connection, or Levi-Civita connection, or metric connection. Metric connection is the better word because we don't talk about torsion. So it's just compatible with this Hermitian form in the sense that if you differentiate the inner product of two vectors, you can do it in every argument together with H in this way. Okay. And D star here denotes the conjugate of the derivation D, defined like that. So everything is standard here. Module together with a connection, and then Hermitian form. And now we have the ingredients to at least define the things we're interested in. So now we just take an algebra, we take two elements in an algebra and module, we take two elements of the module, we take two derivations of the algebra, and we take this data, these four things, we say it's a non-commutative minimal surface in a particular module, namely M, with a Hermitian form and a connection, if the following three requirements are true. So this combination of derivatives on phi is equal to 0, and that is equivalent to the that they are harmonic embedding coordinates. The second one is equivalent to having conformal parametrization, and the third one is something we need to be able to do anything at all, right? Now this, of course, is very general and wild, and you might ask, why do I call it a surface at all, right? So I agree, but we take as much as we need for now, okay? And we need these elements, so phi phi and h of phi bar to be invertible in the algebra. So these are the other components of the metric, so to speak. So this is the definition. Okay. So now let us try to find the tangent module or tangent bundle of our minimal surface, something we would call the tangent module. Okay, to be able to compute the curvature of this module. And we also want to find a connection on the surface to be able to compute things, right? So we introduce the map P. Now, if you look at this one, it includes the inverse of S and T had to do with scalar products of the phis. So you see that this is actually the projection operator, like in standard geometry. When you project from the ambient space vectors onto the submanifold, this will be the projection operator. And if the S and T, if they are invertible, we can write it down in this language as well. Okay. Now you just simply compute that it satisfies that P squared is equal to P, and that is an orthogonal projection with respect to the Hermitian form you have. Okay. And then we also set for convenience, pi is 1 minus p. That is the complementary projection onto the normal space of the manifold, so to speak. And now, for a minimal surface defined by this data, we simply call the image of this projection operator the tangent module or tangent bundle of the minimal surface, in analogy with the geometric expression or geometry in general, right? So. Okay. So
you see M as pullback of like tangent bundle of Rn under embedding, and this is the actual tangent bundle surface.
So you mean if I embed first the ambient space into Rn by embedding theorem?
M is the pullback of the tangent bundle of Rn, perhaps, under your embedding.
If it's a projective module, Yeah, okay, which would be the most natural thing. You could think of it like that, yes. Or in many cases, M is simply itself a free module, yeah. So, now we just continue straightforwardly, I would say. So we now define the connection on this tangent bundle of the minimal surface by simply projecting the ambient space covariant derivative with the projection operator P, okay? Like it works in geometry. And it's, of course, easy to check that it's an affine connection. Everything here is standard computations. And as expected, these elements phi and phi bar that you chose to define the minimal surface, they generate this right A module, Tm. And once you have a connection, of course, you define curvature in the standard way as the failure of this connection to be commutative with respect to two derivations chosen in the algebra. Okay? Good. So now the question is, let me put it this way. I haven't really done much, so to speak, right? I have defined these natural objects. I mean, I just started with choosing two vectors, vector fields, and I compute the curvature and geometry of these two vector fields as they move around in space, right? And of course, I want to demand now that this is a minimal surface, right? That this distribution has some property that connects it to a minimal one. I mean, in principle, you can do all of this without assuming minimal surfaces or so on. The formulas are slightly more complicated, but it's doable. So first of all, let us fit the previous examples we had of the Ennepe surface, of the catenoid, minimal surfaces in R3 into this example, right? To just see how it works. So there we have the Weyl algebra. And we had elements xi, which were Hermitian, and we constructed the phi out of these xi's by taking derivatives of them. And we have two commuting derivations, d and d bar. And they satisfy the last, also this last here equality, which might right now be somewhat mysterious, but it's simply the fact that both of these things are polynomials in lambda, and of course they commute. But you can imagine any algebra satisfying these things, and I can do what I want to do now for these algebras, so it's not so important. So, and what more? The affine connection is simply given as the whatever Grassmannian connection or standard connection on a free module, just differentiating every component. The Hermitian form is the standard one as well on this module, free module. Now, since since phi and phi bar, they are the vectors generating the module we're interested in. So clearly, we are most interested in the components are with phi here and phi bar, and everything else is, of course, written in terms of components. And since we think of d and d bar as the sort of derivations corresponding to the phi and phi bar, like vector field has a corresponding derivation. Now, this connection is not clear here, but we just think of it this way. Then these are the two derivations you would like to plug in here. They are the two most important derivations. So that's why I will now compute these curvatures. You can do it for any derivation, but the formulas are not as nice, and these are conceptually the most important ones. Now, you can compute the curvature now, and it simplifies a lot. You start with this expression on the bottom here, which is lengthy. When you write two derivatives out in this way with the projection operator, two projections operators, and you go on, it's lengthy. But due to the fact that you have a minimal surface and you have fulfilling these things, for instance, commuting derivations, they simplify and they can be written like this. So only in terms of the S and T, which were the off-diagonal parts of the metric in terms of phi and phi bar. Everything else disappears. So it gives you an easy way to compute the curvature. And this is, of course, very analogous to Keller geometry or surface geometry, where you can write these components as logarithmic derivatives, right? d bar of the logarithm of the square root of the determinant of the metric. That's usually the kind of expressions that appear for Cayley manifolds, in particular surfaces. And of course, we don't have the logarithm, but we have sort of performed one derivative here. So we get the s minus 1 ds instead of ln, or d ln s. So they're quite manageable expressions. Okay. So let us now see now of course one asks, what is the curvature then of n-hyper surfaces and the catenoid, or these examples you have provided? Well, the point here with everything also is that, well, you can actually compute these things. They are manageable, they're tractable, so you get a very tractable theory of curvature of these things. So recall, the n-hyper surface was given by this data, together with the two derivations in the Weyl algebra. You can compute S and T here explicitly if you'd like. Now n hat is phi star. Sorry, lambda star. Now if you represent the Weyl algebra in the standard Fock representation, lambda is like the lowering operator, lambda star is like the raising operator, right? A and A dagger. So A dagger, that combination is invertible, diagonal operator. And these combinations are generically, of course, for values of h bar, also invertible operators. So here you see that even though you're not working in the fraction field, but in a representation, as long as these things are fine, S and T are invertible, like in this case, it's okay. You can just go on. And, well, then you simply compute the previous expressions. And you get a one-line or two-line expression like this, with this operator n hat, minus 1, which you compute. And of course, as h bar equal to 0, these two components are equal, as they should be, in some sense in geometry. Okay. So, I want to show you more curvatures of the catenoid. Okay. Now, I won't bother about invertibility and so on, because for this case, it might be quite tricky when you start taking exponentials of unbounded operators and so on. It's, yeah. But just forget about this issue, or do a formal computation, whichever suits you best. You compute S and T now in this way. Remember, sine and cosh can be defined by exponentials. You compute S and T in this way. And you compute the curvature like this. Now I've taken the liberty of writing sort of this algebra elements like this, because everything is a function of lambda plus lambda star, so everything commutes. So the order in which you multiply by the inverse is not important, so I just wrote it like this for visual presentation. And this is what you get, which is similar to the classical expression when h bar is equal to 0. The numerator and denominator are equal, and you can factor 1 out, and it's 1 over 1 plus cosh squared, which is the standard expression for the scalar curvature of the catenoid, right? Okay. So now I want to end with just fitting the standard non-commutative torus into this language. And this is also an example where I don't take the Weyl algebra. Okay, I take the exponential of the Weyl algebra, so you might say it's not a difference, but at least we don't start immediately with the Weyl algebra. We work entirely in the algebra of the non-commutative torus. Sorry for A and B, by the way. U and V were taken, and the S and T were also taken, so I had to think of something else. So the algebra of the non-commutative torus, they're given by unitary operators A and B, such that when you flip them, you get a Q, which is a complex number with absolute value 1. Okay? And the Clifford torus, the classical Clifford torus, is a minimal surface in S3, not in Rn or R4, but in S3. So therefore, we don't want to take the free module as an embedding space. We want to take something else. So I want to take this example now to show you that you can do other things than just free modules, if you want. So we have to find a module in this language corresponding to the tangent bundle of S3. Okay. So, but for the Clifford torus, we know how to write the normal to the Clifford torus, the normal in S3, the normal in in R4 being normal to S3. This one we know how to write. And now this A star plus A, those of you who have done this a lot, they correspond to sines and cosines, right? So this combinations correspond to sines and cosines, and this n corresponds to the normal vector in R4. Since we have the normal vector, we can define a projection simply by taking the 2 times the normal vectors like this as a projection of an unit vector looks like. And this is on the free module A4, and you check that it since now ni, this sum is equal to 1 because they are unitary operators, it holds that it's a projection operator. Okay. So we simply define our ambient space module to be 1 minus this projection, because this is the projection onto the normal space, and let it act on A4. This is our M, our ambient space now, not the space of the minimal surface. Right, this is what I said. Corresponds to the tangent bundle of S3. And the Hermitian form on this M is simply the restriction of the standard form on the free algebra. And the connection is simply given by the projection of the Grassmannian connection of the free module. Okay? This is the data we start with. Module M, like this, the projective module, and with the standard Hermitian form and affine connection. And then we define phi, and this is an expression which is, again, in complete analogy with classical geometry, that you get the sine and cosines you want to embed the Clifford torus into S3. And you take this and you take the conjugate, phi bar, and you take these 2 derivations, which are complex combinations of the standard Hermitian derivations of the non-commutative torus here. That's the standard derivations, right? And you check now that, first of all, these phi's are actually elements of M. They're, of course, elements in the free module, but they have to be elements of M. You check that. You check that the parametrization is conformal, that this scalar product is 0. And you check that these 2 that are individually 0, and therefore also, of course, their sum is 0. And this S and T, which you need to define the projection operator, they're just being equal to the unit. And if you compute the curvature now with all these definitions, you simply get that the curvature here is 0, as it should be in some sense for the torus. So it's so now what do I want to say with this? I want to say that it might be that if you find data of this type that is actually gives you nice geometry which is tractable. And why is it nice? Well, I hope that it's nice because it has many analogies with classical minimal surface theory. In classical minimal surface theory, they're theory of very particular surfaces. There are many things that hold for minimal surfaces. And since there are so many similarities, I hope I already shown you many things that are analogous, but maybe there are even more things that can be proven in this context. So let me just...
Sorry, this Clifford torus, you mean is an isometric embedding of flat torus?
Into S3.
Into S3.
Right, right.
But you have other embeddings. You have usual embedding, which has more interesting curvature.
Sure. I mean, right.
Can you complete that as well?
Well, well, you have to pick. In principle, yes, but you have to. Well, so what algebra am I using? And of course, for compact things, you don't want to use the Weyl algebra because it's. Sorry.
The algebra that you are using is not on the torus.
On a compact torus, right? But it's e to the Weyl algebra, right? So that's fine in that sense.
So the ambient space is non-commutative too? I don't understand.
The ambient space is.
Also non-commutative in your case?
Well, there is no ambient space. There's just an ambient module over the same algebra. Okay. So there is a fixed algebra, and the ambient space module is over this algebra as well as the tangent bundle of the minimal surface. Okay.
Is it possible to do the same construction with a canonical module over the
Right, but these... yeah. Right. Well, yes and no. I mean, my first reaction would be, well, they are not the modules that are the tangent space, tangent bundle of the torus, right? But they also the free module on two generators. Yeah. So it's not. But of course, you don't. In this setup, you can. I mean, generalized this concept, so you might think of other things that are not at all related to the real tangent bundle of the manifold, to give you something nice which is tractable and computable, right? So this I don't know, but that's my hope also, that I can do other things. Okay, so let me sum up, and I will actually make the 55 minutes I had. That's good. So what did we do? So we started by proposing a definition of non-commutable minimal surface in the Weyl algebra, by saying that there's a tuple of elements. Each element has to be harmonic in some sense, and the parameterization has to be conformal of this minimal surface. And it was very naive, but already this naive definition gave you a representation theorem for all such tuples of length 3, right, that you can find, which is the Weierstrass representation theorem, right? And as I also said many times, the original motivation was to produce solutions to certain equations, right? So in this way, you can produce many explicit examples that you can play around with, maybe have nice properties that you can study and so on. Which I think is interesting in itself for doing some kind of non-commutative geometry, that you have many examples to which are tractable that you can play around with. I try to generalize this and put it in a more algebraic language, and in this way you could think of it in geometry as formulated that picking two vector fields in your ambient space manifold and trying to look at the geometry of these two vector fields and adding the condition that these two vector fields actually come from a minimal surface, the tangent bundle of a minimal surface in some way. Okay? Which allows for also compact minimal surfaces, which are not possible in Rn. You have no compact minimal surfaces in Rn. So if you want compact manifolds, you have to do something like this. And I showed you an example that you can actually put the non-commutative torus into this, which is sort of compact in some sense. And my motivation is also that you get something tractable. You can compute these things. And now we can go on, and you can ask about, of course, all the other geometric stuff like cohomology and whatnot that you want to study. And are they nice? Can you prove some theorems? Because that's what's in the end justifies your definition, right? That you can prove something with it. And so I hope to continue this. And here I stop. Thank you.
Would you have any examples where so all the examples you gave were sort of taking a commutative minimal surface,
right.
Sort of not taking
Mm-hmm.
Do you have any examples where you have a non-commutative minimal surface which does not seem to come from some commutative minimal surface?
Have not tried. Of course, that's well. Also, the non-commutative torus, of course, comes from comes from just the standard. So, which is, of course, in many ways, this is how we think about manifolds, construct manifolds, non-commutative geometry. You take all these analogies, and I don't know. It's interesting. I also already in some commutative problems with Poisson brackets, and so it's interesting to know what happens if you have a finite dimensional algebra, for instance. Can you find such finite dimensional algebras? What do you get, and what is the curvature in that case, right? I don't know, but it's interesting. Yeah.
But I have a problem calling it theory of curvature, because curvature is an intrinsic theory. I mean, this is very much depends on all this extra baggage you brought in.
It is. No. This I know. I in some way I agree. In another way, not, because you could ask the same thing for geometry, differential geometry. Okay, you compute anything. You pick any paper in differential geometry, and they consider a manifold. They compute things on it. How do you do it? Well, it is an embedded manifold almost every time.
There's
So
no problem with that, but then you prove that it's independent of coordinates and all choices.
right, but that's right. So first of all, for computational reasons and analogy reasons, I tend to see it also as a feature, not only a drawback, right? On the other hand, you're right. So you should look at picking the xi's as picking a metric on your manifold. So in this sense, you can think of, you don't have to think about embedding. You can just think of it as a way of picking a metric.
At one stage, you also have to assume that there is a compatible connection. So if you prove that for every metric there is a unique compatible connection, then
Right.
there is something you can go on. But,
Right.
but you assume the existence of that as well.
In the ambient space. No, not on the surface. If you have it in the ambient space, you get it in the surface, on the surface.
The ambient space, of course, there is always one.
If you pick Rn, there is always one, you're right. So in this sense, it's like doing submanifold theory. It's not less general than manifold. So, but no, I understand your point, and I have the same. There is a small, but I think there are many advantages as well.
For example, something like theorem or equilibrium, I mean, you prove something like that.
Right.
You know, that's what Gauss did.
Right. This.
You embed and
Right.
then
Yeah.
you have theorem or equilibrium.
Yeah. No. This right. So this you can think of. You can slightly perturb the embedding, right? And you can compute, for instance, the scale curvature, and assuming you have a trace in your algebra, whatever, you can trace this and see, is this independent of this perturbing thing, how you embed it. And I agree, these kind of questions now are interesting to see because they would, as you say, justify the definitions. I completely agree. Yeah.
Last question. I think you might also need some assumptions on this ambient module and its metric, because I think you can always take a manifold, embed it in itself, and then it's probably minimal by definition in itself, and you learn nothing about so any surface is minimal in some sense.
Right, but no, it's the terminology. It's a minimal surface in a certain module.
Exactly.
Right. So you have to.
Itself, you learn nothing about it.
Sure, I agree.
Your module that you use to begin with as your large module is completely arbitrary. Any surface would do. So you're just looking at non-commutative surfaces, and now you have some way of, if you start with some nicer module and some nice metric on that, you can say that this surface also has some reasonable curvature, maybe because your ambient module is nice, but if your ambient module is completely arbitrary, I think you probably have a completely general situation because...
Well, you can do these computations to get the short formulas for the curvature anyhow. But
because you have surface, not because something nice is happening, because any surface should be treatable in principle.
Well, in principle, that's one of my points here. These are not just in principle computable; it's very computable. It's very computable, and these are it's sort of similar to the question about embedding of the ambient module. So how should you do it? And I mean, I personally have no complete picture of this. No, I have no complete picture. But I seem to think that there are some advantages to having the embeddedness as well, because you can do many things.